Hi everyone. So as always, these are the learning objectives. Right now, just reading through them, you will have absolutely no idea what I'm talking about. So what I recommend is that you just wait until the end and you'll see that we've covered all this. But if you don't want to, then feel free to copy those in your notebook and go through them as we go through the lesson. So today we're mainly going to be talking about something called a relay. And this thing here is a relay. Now, a relay is basically an electromagnet. So remember, this is an iron core and this is just some wire that goes around it. And remember that when there's a current that goes through here, then this creates a magnetic field that goes like that. And, well, that's just like a magnet. That's why it's called an electromagnet. And the idea is that we use this as some kind of switch. Now, how exactly do we do that? Well, do you see how now this switch is open? Because this is open, there's no current going through here, so this is not a magnet. This is just a chunk of iron. Because this is just a chunk of iron, there's this other iron piece here that's connected to this other circuit, and this iron piece is not moving at all because it's not being attracted by this or anything. And therefore, this switch here is open. Now imagine that I close this circuit and then some current starts going through here, so this starts creating a magnetic field. Because it creates a magnetic field and this is made of iron, this is going to be attracted this way. And when this happens, this is going to move this way and this switch here will become closed. So this circuit here will also become closed and will start working. Now you're probably thinking, why would I do this? I mean, why don't I just put this switch in here instead of doing all this really terribly complicated stuff to open this switch? And the reason is that sometimes you have a circuit with a really high voltage and you really don't want to put a switch in it where you are going anywhere near that with your finger because that's dangerous. So what you do is you take this other circuit that has a much lower voltage here, which is perfectly safe to switch on and off, and then you use this circuit to switch the big circuit with a lot of voltage on and off through a relay. Now, as you can see, in this relay by default is open. So this switch here is open. And we call this thing an always open relay. Or sorry, normally open relay. So this would be a normally open relay. Now we could, for example, place this thing in here so that the effect would be exactly the opposite. When there's no magnetic field, then this thing would be closed. When there's a magnetic field, this opens the circuit. So this would be a relay that's normally closed and then opens when we switch this on. And in this case, we would have a normally closed relay. Now, because drawing all this stuff is a pain, we normally use one of these little circuit symbols that are very easy to understand and very easy to draw. So let me just show you how we normally draw this. So first I'm going to show you how a normally open relay looks, and then I'm going to show you how a normally closed one looks. So here's our current. This is a coil. See, much easier, right, to draw a square than what I did. And then this is our switch. And then we see that this thing is going to be open unless there is a magnetic field through here, and then this thing is going to close itself. So this is a normally open relay. Now for the normally closed relay, it's very similar. We still have a coil, but what happens is that we have something like this. Oh, well, that's supposed to be here. And then this is a closed switch. And what happens is that when we switch this on, then this will attract this little thing over here, and like this, it will open the circuit. So this is a normally closed relay. Now you may be wondering, that's a lot of complication simply to switch things on and off. But the real power of a relay comes when we attach it to other components, such as a thermistor or light-dependent resistors. Now, does anyone remember what a thermistor did? So we had something that looked like this. So, like that. And this meant that this resistance depended on temperature. So normally this will have very high resistance, and then the moment that this starts getting heated up, this has less and less resistance. So more and more current will go through it. Now let's see how we can use this to make a fire alarm. So let's zoom out. And as always, we will have some kind of power source, whatever it is, and that's going to be connected to our thermistor that, again, looks like this. Keep forgetting. And then we're going to connect this to a normally open relay. So here's our relay, and here's our circuit. So little triangle. Okay. And now let's see what happens here. Now let's imagine that this circuit here turns off the alarm. So this goes to, well, this has a power source and goes to a buzzer. Now, when the temperature is low, this thing has very high resistance. Therefore, the current going through here is very small. Therefore, this is attracting this very little. So this is still open. When, for example, there's a fire and this thing gets heated up more and more and more and more, the current starts going up so that this becomes stronger and stronger and this gets pulled more and more. There is a limit at which, if the temperature of this thing becomes high enough, this will have much less resistance, much more current, this will be much more powerful, and it will finally close the circuit, and then the alarm will go off. So this is a way that we can make sure that when things get very, very hot, people actually know about it and don't die in a fire, which is always nice. Now, we can use this same idea to make, for example, a building that automatically turns the lights off during the night and on during the night and off during the day. So how would we do this? Well, again, we would need a circuit, and this circuit would have a light-dependent resistor, which, remember, looks something like this. And after this, we need to add a relay. And now I'm going to give you 10 seconds to think about whether this relay should be normally open or normally closed. Remember, this thing here, when there's lots of light shining on it, the resistance goes down. So we have more current, and then this thing will become more powerful. And what we want is there should be lights on when there's no light. There should be lights off when there's light. So 10 seconds to think about it. Now, hopefully you did that and you realized that when I have no light in here, then there's very little current, and what I want is the lights to be on. So really what I want is a relay that is normally closed. Why? Well, let's just draw it and we'll see why. So I have, again, my relay goes like this, and then like this, like this, like that. Okay, now what we see is when it's dark, this is not very powerful, so the lights are on. When there's light, this becomes very powerful and opens the switch, and therefore we don't have any light anymore. And of course, this circuit here would continue to some power source and then some light bulbs or whatever. So you've seen how we can use a relay to, for example, have a building that automatically switches off and on the lights, something that triggers a fire alarm, and we can also use it to switch off and on things that would otherwise be dangerous to switch off and on with a switch. Now, we need to talk about the magnetic force in a current, and this will be hard to understand because the magnetic force works in a really bizarre way. So, just don't panic. It's not that hard, it's just weird. So let me just show you what I mean. So Ampere discovered that if you had two wires, so imagine that these are my two wires. And what he found out is that if I had a current flow going through this one, and they're going through this one, they would actually attract each other. So this wire would go this way. This means that this wire here is doing a force on this wire that goes this way. Now, remember that we've been talking about magnetic fields, and that using the right-hand rule, we can know that this thing creates a magnetic field that goes around it like that, and the magnetic field points like this. And of course we can make this so bigger and bigger, so there's like these concentric circles that go like that, right? So the magnetic field goes around this thing like that. And of course, therefore, there is a magnetic field on this that goes into the page. So there's a magnetic field that's pointing this way, and remember this is like a 3D representation. So this thing is going into the page. So realize that this magnetic field is going into the page, but the current here is going up. So we have, let me just show you. So magnetic field going into the page. This little cross just means it's like an arrow, but I see it from the bottom, right? So magnetic field going into the page, then the current's going up. And where's the force going? Well, the force is going this way, right? Because this is being pulled to the left. So we have the force goes this way. Now, how bizarre is that? You can see that the current and the magnetic field and the force are perpendicular to each other. So none of them, well, two of them are in the same plane, but like 90 degrees, 90 degrees, 90 degrees. And this always happens. It turns out that if I want to calculate the force that a magnetic field does in a current, the force is always perpendicular to both the magnetic field, the current. This is really bizarre, and in order to understand this, you would have to know relativity. So I don't recommend trying to understand this. It's just the way it is. It's really weird. Just remember, the magnetic force is strange. It's perpendicular to the field and perpendicular to the current. Now, thankfully for us, there's a rule that allows us to always be able to figure out where the force is pointing if we know the current and we know the field. And that's what I'm going to show you right now. So first let me zoom out. And this picture that appeared out of nowhere, this is called Fleming's left-hand rule. So let me just write that down here. Let's hopefully it will be visible. Fleming's left-hand rule. And it's called Fleming's left-hand rule because it was a guy named Fleming that came up with it, and because it uses your left hand. So remember, this uses your left hand as opposed to the magnetic field thing that uses your right hand. So remember that when we wanted to know how the magnetic field was pointing around here, we used our right hand, but for the force, we use the left hand. If you mix these two up, you will get a wrong answer. So please remember, different hands, okay? Anyway, the idea is that if you take your left hand and pointing like this, then the force points in the direction of the thumb, the magnetic field points in the direction of your index finger, and your current points in the direction of your middle finger. And you basically just have to memorize this. If you use this consistently, you will always be able to know where things are pointing. So for example, imagine that I have a current that goes this way. So this is my wire, current goes this way. And then I have a field that goes this way. So then what I need to do is use the left-hand rule. Now the current is my middle finger. So, well, you can't see me, but I'm doing this with my middle finger. And then the magnetic field is my index finger. Therefore, oh, man, that's complicated. I have that the force has to point inside the page. And if you do this yourselves, you will learn a lot from this, and you will also realize how awkward this is, and you will also realize that if you do this during the IGCSE exam, you're going to look, pretty weird, but that's what you need to do. So, there you go. Now you might be thinking, why are we learning this? Well, we're learning this because the magnetic force on a wire is extremely useful, and it's the way that electric motors operate. So for example, every time that you dry your hair with a blow dryer, you're using a DC motor. Every time that you use, anything that moves like a mixer, you're using a DC motor. So the DC motor is what allows us to make things move with electricity. So that's why it's so important. Now, the basic idea of a DC motor is that you have a magnet and you have a coil placed in that magnetic field. That's supposed to be in like 3D, so imagine it as going to the page. Now, it turns out that this part here makes absolutely no difference because this part here is in the same direction as the magnetic field. And because they're in the same direction, when the current and the magnetic field are parallel, there's no force. Because remember that the force has to be perpendicular to both the current and the magnetic field. And if these are both parallel, then things don't work out. So what we have is that there's going to be a force on this and this. And now what we need to do is use Fleming's left-hand rule again and figure out where this is going. So now again, I'm looking very stupid and hopefully nobody's seeing me. And by using Fleming's left-hand rule with this part, I can conclude that there's a net force that goes up. And if I do the same thing here, basically I'm just gonna have to turn my hand around. So what's gonna happen is that there's going to be a force down. If you don't believe me, please do this yourselves. It's very important that you know how to do this. So what's gonna happen? Well, if I press this up and I press this down, what's gonna happen is that this coil is gonna turn. And that's great, because if I can make things turn, then I can make things move, because I can attach this to a wheel, for example, or I can attach this to a fan, or I can attach this to whatever I want. So this is really cool. Now, this is the basic idea. However, it has a little problem, which is when this has turned until here, then what happens is that things reverse, because now this current is going the other way. This current is going the other way. So what we have is a coil that does this, and that's not what we want. We want a coil that turns all the time. And that's why we use something called a commutator. And the idea of a commutator is this. Let me just draw it for you. So these two wires, actually I'm going to remove this thing. So these two wires go to something called, to these weird rings that do something like this. Okay, so this is a ring, and this is another ring, and these things are rotating. And these rings go to the power source. And you may be wondering, why on earth are we doing this? Well, here's why. Because this is connected to here, and then the ring is connected to this, then this will create a current that goes this way. Now, when this has reached the point where it's already about to turn, this will go to the other ring, and then the current direction will reverse. And because the current direction will reverse, we're still going to get a pull this way and a push this way. So instead of doing this, the whole thing's going to keep turning. So the basic idea is we have these two things which are connected to the battery, and then these parts of our cables are rotating around this, so that the current is always changing directions, so that finally we can get a circular motion. If you found this really hard, I don't blame you, and I will be more than happy to revise this with you in class. We call this thing here a commutator. So commutator. And the reason it's called a commutator is because it makes things commute. Remember that when you commute from your house, it means that you're going back and forth, right? So this thing makes our current commute. First it goes this way, then it goes this way. First it goes this way, then it goes this way. Every time that it changes ring, it changes direction, so it makes the current commute. Okay, so that's pretty much it. Let's see if we've done all of that. So first thing, describe the action of a relay. We've done that. Remember, it's this electromagnet that is connected to this switch, and then when the electromagnet, there's current flowing through it, then the switch closes. When there's no current, then the switch opens. Recognize and demonstrate understanding of circuits operating as light-sensitive switches and temperature-operated alarms using a relay. Remember that we connected the relay to, for example, a thermistor. When the temperature went up, the resistance went down, the current went up, and then we had the electromagnet started to work and then closed the circuit or opened it. Finally, state and use the relative directions of force, field, and current. That's Fleming's left-hand rule, which hopefully you have written down in your notebook and memorized. And finally, explain the operation of the DC motor, which is what we just did. There's lots of things to practice. We will do that. Don't panic. I know some of the things we did today are a little weird. The problems don't get very, very, very hard. This is mostly about memorizing and using the theory that you learned. So good luck, and I'll see you in class.